The first derivative test. The first derivative test states, suppose f is differentiable on the open interval from a to b, except possibly at c, where c is the critical point. If f prime, which is the derivative, changes from positive to negative at c, then we say that f has a local maximum at c. Graphically, if f prime, which is the derivative, is positive, then the graph rises to c, and then negative means it falls from c. So that would tell you that the point c is a local maximum. Second bullet, if f prime changes from negative to positive at c, negative would mean that the graph is falling, and then it rises afterwards. We see that we have a local low point, so we say that f has a local minimum at c. If f prime does not change at c, then f does not have an extreme value at c. Graphically, that could look like a graph. Let's have an xy plane. Think of a cubic. That is, if y equals x cubed, that graph would rise to the origin, and then it would continue to rise. While you have a horizontal tangent line at x equals 0, the graph continues to rise, so it's neither a maximum nor a minimum. Similarly, if you were to say look at a graph of the negative of x cubed, the graph of that function would fall to the origin, have a slight horizontal asymptote, then continue to fall some more. Again, you'd have a horizontal asymptote, but the sign of the derivative in the interval from negative infinity to 0 and from 0 to positive infinity remains the same, so c would not be a local extrema. Example, use the first derivative test to find any local extrema of the function f of x equals x to the fourth minus 4x cubed plus 12. To solve this, we always begin by looking at the domain of the function. Let's observe. The domain of f is all real numbers because f of x is a polynomial function. So domain of f is all real numbers. Now, the next step in finding local extrema is to find critical points. You find critical points by first finding the derivative and determining the x values for which the derivative equals 0, or where the derivative might be undefined. Let's find the derivative. F prime of x is equal to, bring the 4 and make it a coefficient, so we've got 4x and the power is 4 minus 1. That would be 3, minus the derivative of 4x cubed, bring the 3 down to the coefficient and multiply it to the 4, so that would be 12x, and then 3 minus 1 is squared. The derivative of 12 is 0. What we want is to find where this derivative equals 0. There will be no place at all where the derivative would be undefined because the derivative function is also a polynomial. So let's solve 0 equals. Now what's common? 4 is common to 4 and 12, so we can factor out the 4. There's an x cubed and an x squared, so the largest x power would be x squared. Factor out 4x squared, and what you've got left is x minus 12 divided by 4 is 3. X squared divided by x squared is 1. This is exactly the same thing as saying 4x squared equals 0 and x minus 3 equals 0. So we get critical points at x equals 0 and also at x equals 3. These are the critical points. Now let's make a sign chart number line. This is where we apply the first derivative test. So for the sign chart number line, I'll write f prime and then draw a number line. The f prime is to the left and above the number line, and below the number line I'll write x for my x values. When x is 0, the derivative is 0. When x is 3, the derivative is 0 as well. Now we are going to evaluate each of the 3 regions of this number line in the derivative. Pick a number less than 0, like -1. It's okay to write this out. You could write, because we want to know the derivative evaluated at -1. We could put it in the factored form, so you got 4 times -1 squared times -1 minus 3. Now look what I'm going to do that's very efficient. -1 squared is positive. So I've got a positive with the 4 times the positive with the -1 squared. However, -1 minus 3 is negative, so I'm just going to write that this equals a negative number, because that's all I'm concerned about. In this region, from -infinity to 0, the derivative is negative. Let's evaluate at a region between 0 and 3. So how about if I just pick 1? Take the derivative and evaluate it at 1. That's 4 times 1 squared times 1 minus 3. 4 is positive times 1 squared is positive. So positive times 1 minus 3 is negative. That region is also negative. Now pick a number to the right, the rightmost region, so the right of 3, I'll just pick 4, and evaluate that in the derivative. You'll have 4 times 4 squared times 4 minus 3, and so you're going to have a positive factor of 4 times the positive factor of 4 squared times the positive factor of 4 minus 3, which is 1. Positive times positive times positive is positive. The first derivative test tells us where the region for the derivative is negative, the graph is falling. So the first region, it's falling. In the second region from 0 to 3, it's still falling, but then it rises. It has a turning point when x equals 3. So the graph rises after the other side of 3. Let's use the first derivative test to write the answer. The sign of the derivative changes from negative to positive at x equals 3. Therefore, by the first derivative test, f, not the derivative, but the function f, has a local minimum at x equals 3. Example, use the first derivative test to find any extrema of f of x equals 15 times x to the power of 2/3 minus 3 times x to the power of 5/3. Again, when we start this problem, identify the domain. The domain of f is going to be the set of real numbers. There are no even roots and no variables in the denominator, so the domain, we'll say, is the set of real numbers. Now we are ready to begin looking for critical values. To find critical values, We are looking for the x values where either the derivative equals 0 or the derivative does not exist. To find the critical values, we've got to first find the derivative. Let's do that. F prime of x is equal to, we have the constant of 15, and then the derivative of x to the power of 2/3. Bring the 2/3 down, write it as a coefficient, x to the power of 2/3 minus 1. That's going to be a negative 1/3. And then we have minus 3 times the derivative of x to the 5/3. We bring the 5/3 down. That becomes the coefficient times x to the power of 5/3 minus 1 is 2/3. Let's continue to simplify this. 15 times 2/3 is 10 as the constant. And let's move that negative 1/3 power into the denominator so we can write it as positive 1/3. Then we'll have minus 3 times 5/3 is 5. And we still have x to the 2/3. In order to add or subtract fractions, we need a common denominator. So here our common denominator would be the x to the 1/3. This will be 10 divided by x to the 1/3 minus, ooh, look what nice thing happens. X to the 2/3 times x to the 1/3 is just x. Got rid of that fraction. And the denominator, we still have x to the 1/3. And so at this point, we can say that the derivative of this function is 10 minus 5x in the numerator divided by x to the power of 1/3. Continuing with the derivative of f prime of x equals 10 minus 5x divided by x to the power of 1/3. We need to solve for x value such that the derivative is either undefined, so does not exist, or the x values where the derivative equals 0. Let's begin with the easier one, which is the derivative is undefined at x equals 0. Why? Because at x equals 0, the denominator would be 0. Now we're going to solve for where the derivative equals 0. So to do that, we'll have 0 is equal to our derivative function, 10 minus 5x, and I'll go ahead and write x to the 1/3. When you're solving for a fraction to equal 0, you only set the numerator equal to 0, because if the denominator equals 0, it's not even defined. So to solve this, we're going to say that 0 is equal to 10 minus 5x. Again, I'm not ignoring the x to the 1/3 in the denominator. I'm saying that it doesn't have a part here because we want the fraction to equal 0, and for that to happen, only the numerator can equal 0. Let's solve for x. If you see that it's 2, that's perfectly fine, but if you want the work, you can do 5x equals 10, and then solving for x, you get x equals 2. Now we have two critical numbers, and we're going to do a sign chart number line. F prime, draw our number line, and I write x below it. I'll indicate that when x is 0, the derivative does not exist, and when x equals 2, the derivative is 0. Now again, all we need are the signs for the derivative in the intervals. We're not concerned with the numbers, just whether or not it's positive or negative. So let's do that. Let's pick a number to the left of 0. So let's compute the derivative at -1. Put in -1 every place you have an x in the derivative function. That would look like 10 minus 5 times -1 divided by the cube root of -1. And you see 10 minus 5 times -1 would be 10 plus 5. You got a positive over a negative. So the sign of the derivative in that region is negative. Let's evaluate in the region between 0 and 2. So I evaluate the derivative. 1 is a nice number between 0 and 2. Put that in the derivative function. You got 10 minus 5 times 1 divided by the cube root of 1. And that's 10 minus 5. That's a positive number divided by the cube root of 1 is also a positive number. And so in that interval between 0 and 2, the derivative is positive. Do this one more time. So we need to evaluate the derivative for the sign in the third region. So let's do this. Oh, a number to the right of 2 might be 3. That'll work. Then you got 10 minus 5 times 3 divided by the cube root of 3. Well, the denominator is positive. It'll be a small number. But the numerator, 10 minus 15, that's negative. So the region to the right of 2, the derivative would be negative. If the derivative is negative, the graph is falling, the function is decreasing. If the derivative is positive, the graph is rising, the function is increasing. To the left of 0, the derivative is negative. To the right of 0, the derivative is positive. That tells us we have a local min at x equals 0. Now let's continue to move. To the right of 2, the derivative is negative. That tells me the graph is falling. Function is decreasing. So if you rise to a point and then fall afterwards, that's a high point, and we would call that local max. Let's write this out neatly. By the first derivative test, f, that's the function, not the derivative, f has a local min represented by 0 and the function evaluated at 0. The 0 tells you where the min is. The f of 0 tells you what that value is. Let's write this for the local max as well. By the first derivative test, f, not the derivative, f, the function has a local max, and the ordered pair would look like 2, and the function evaluated at 2. And let me stress again, 2 is where the max happens. F of 2 is what that function value is.